This is the first close-up photograph of Pluto ever taken. It was captured by a NASA spacecraft called New Horizons on July 14, 2015, after a journey of 5 billion kilometers. And this is what stunned NASA. Parts of this surface are younger than some forests on Earth. Now, the problem with Pluto is that none of this was supposed to be happening. A world this far from the Sun should have frozen solid billions of years ago and never changed again. But that is not what New Horizons found. What it found was something far stranger. Before New Horizons, Pluto was barely more than a dot. Even through the Hubble Space Telescope, the best images we had showed nothing more than a blurry smudge with faint variations in brightness across its surface. Light patches here, dark patches there. That was it. But those faint variations were actually the first hint that something interesting was going on. Pluto's atmosphere was first detected from the ground during a stellar occultation on June 9, 1988. As Pluto drifted in front of a distant star, the star's light didn't vanish abruptly the way it would behind a bare, airless rock. Instead, the light dimmed gradually, which meant Pluto had an atmosphere, a thin one, but it was there. And then something curious showed up in the data. There was a knee in the light curve, a point where the starlight dropped more suddenly than expected. Some researchers thought this was evidence of haze or aerosol particles floating in the lower atmosphere, scattering and absorbing the light. Others argued it was just a sharp temperature drop near the surface. Either way, it was clear that Pluto's atmosphere was doing something unusual. Subsequent stellar occultations from 2002 to 2015 found more evidence of atmospheric waves and confirmed that both aerosols and a steep temperature gradient were likely present. The wavelength dependence of the starlight matched what you'd expect from tiny, submicron particles absorbing less at longer wavelengths. But from billions of kilometers away, with only pinpricks of starlight to work with, there was only so much we could learn. What we needed was to go there. The New Horizons spacecraft launched on January 19, 2006. It was the fastest object ever sent into space by a human. And it needed to be, because Pluto is very far away. Even traveling at over 50,000 kilometers per hour, it took 9.5 years to get there. On July 14, 2015, New Horizons flew through the Pluto system. Now here is the thing about a flyby mission at the edge of the solar system. You do not get second chances. A signal from Earth takes 4.5 hours to reach Pluto, so no commands could be given to the spacecraft during the encounter. Every observation had to be pre-planned and automated. The close proximity science window lasted only a matter of hours and was largely restricted to one hemisphere. But in those hours, New Horizons captured images that stunned the world. Pluto was not a dead, frozen wasteland. It was alive. The surface was staggeringly diverse. Enormous glaciers of nitrogen ice, towering mountains of water ice, wide plains that looked freshly resurfaced. Active geology on a world where nothing was supposed to be happening. And at the center of it all was a feature so striking, so unexpected, that it became the defining image of the entire mission. A heart. A vast, bright, heart-shaped region stretching across nearly 2,000 kilometers of Pluto's surface. It was the first thing the cameras resolved clearly, and it immediately became the most iconic image from the outer solar system. But this was not just a pretty shape. Inside that heart lay evidence of geological processes that had no right to be happening on a world this small, this cold, and this far from the sun. The heart-shaped region is called Tombaugh Regio, named after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. But it is the western lobe of that heart that holds the real story. That region is called Sputnik Planitia, named after Earth's first artificial satellite. Sputnik Planitia is a massive basin, roughly 1,400 by 1,200 kilometers across. It sits mostly in the northern hemisphere, but extends across the equator. And it is filled with glaciers of nitrogen ice, bright and smooth and unlike anything else on Pluto's surface. Now here is the strange part. When scientists looked closely, they found that much of Sputnik Planitia is divided into irregular polygons separated by shallow troughs, averaging about 33 kilometers across. These are not cracks or craters. They are convection cells. The nitrogen ice is actually moving, flowing in slow, churning currents driven by heat from Pluto's interior. Warm ice wells up in the center of each cell, spreads outward, cools, and sinks again at the edges. The convection cells have about 100 meters of vertical relief, with the highest points at their centers. Models suggest the nitrogen ice is about 3 to 4 kilometers deep and flows at roughly 7 centimeters per year. Scientists have estimated a surface age for this region of about 180,000 years. On a world that is over 4 billion years old, that is practically brand new, no impact craters were found anywhere on Sputnik Planitia. None. The surface is being constantly renewed. So what created this basin in the first place? The leading theory is that it originated as an ancient impact site, gouged out by an object estimated at 150 to 300 kilometers across. Over time, nitrogen and other volatile ices accumulated in the depression. The basin's lower elevation meant higher surface pressure, which raised the condensation temperature of nitrogen, making it a natural cold trap. More ice collected, which increased the albedo, which cooled the surface further, which attracted even more ice, a runaway process. And then something even more remarkable happened. The accumulation of all that dense nitrogen ice created a positive gravity anomaly. Sputnik Planitia became heavy enough to actually reorient the spin axis of Pluto, a phenomenon called polar wander. Pluto literally shifted on its axis to put this heavy basin near the Pluto-Charon tidal axis, the most energetically favorable position. Today, Sputnik Planitia sits close to the anti-Charon point on Pluto, and researchers have calculated there is less than a 5% probability of that happening by chance. But here's the thing. For the gravity anomaly to work, you need something dense beneath the thinned ice crust. You need liquid water pushing up from below. You need an ocean. Sputnik Planitia does not exist in isolation. The landscape surrounding it tells its own story. On the northwest edge, a chaotic cluster of blocky mountains called Al-Idrisi Montes may have formed when adjacent water ice highlands collapsed onto the Planitia. To the southwest stand the Hillary Montes, rising 1.6 kilometers above the surface, and further south, the Tenzing Montes, which climb to 3.4 kilometers. Named after the first climbers to reach the summit of Everest, these mountains have a fractured, jumbled character that hints at violent geological processes. Within the basin itself, you can find clusters of blocky hills, each one to several kilometers across, collecting in aggregations up to 20 kilometers wide at the margins of convection cells. These may be floating chunks of detached water ice crust, carried out onto the Planitia by glacial flow and herded into the troughs by the slow churning of nitrogen ice below. The eastern lobe of Tombaugh Regio is different. It is an upland of sublimation-pitted methane ice, carved by eroded valleys filled with nitrogen ice glaciers that appear to flow down into the main body of Sputnik Planitia. At the eastern edge lies one of the most alien landscapes ever photographed, the bladed terrain of Tartarus Dorsa. Here, the surface is covered by ridges hundreds of meters high, separated by long, narrow valleys, all topped by blade-like formations of methane ice that resemble penitentes, the spiky ice formations found at high altitudes on Earth. But Pluto's penitentes are 2 orders of magnitude larger than anything on our planet, a testament to the extreme power of sublimation on this world. Around Pluto's equator lies a dark band of maculae, low albedo regions coated in tholins, those reddish organic particles that rain down from the atmosphere. Tholins are deposited globally on Pluto, but volatile ices disrupt them everywhere except at the equator, where relatively mild temperature changes allow the tholin layer to persist undisturbed. The water ice that forms Pluto's bedrock can be seen in only a few places, along chasm walls and on the exposed sides of tilted ice blocks, layered with red tholins. Methane and nitrogen ices cover most of the surface, but they are just a veneer. Beneath it all, the rigid skeleton of Pluto is water ice. For a long time, the standard assumption about Pluto was what scientists call a cold start. The idea was simple. Pluto formed from cold material out in the distant Kuiper belt, and its interior stayed frozen for billions of years. Radioactive decay in the rocky core slowly generated heat, and eventually that heat melted some of the internal ice, creating a subsurface ocean sometime later in Pluto's history. If that were true, Pluto's surface should show signs of compression from early on, when the ice was melting and the interior was contracting. Then, more recently, you'd see extension features as the ocean began to refreeze and expand. But when scientists examined the New Horizons data, they found lots of evidence of extension across Pluto's surface, and no evidence of compression. None at all. So in June 2020, a team of researchers from UC Santa Cruz proposed a different idea: a hot start. In this scenario, Pluto formed rapidly, in less than 30,000 years. The gravitational energy released during that violent accretion generated enough heat to create a liquid ocean from the very beginning. Pluto was born with an ocean, and that ocean has been slowly freezing ever since. The hot start model predicts extension throughout Pluto's entire history, which is exactly what the surface features show. Ancient ridge and trough systems suggest early extensional tectonics, while more recent faults record ongoing extension. The total amount of strain matches what the models predict. Now, if Pluto started hot, that raises a bigger question. If the ocean has been there for over 4 billion years, what has kept it from freezing solid? The answer, it seems, lies in a thin layer of something unexpected: methane clathrates. These are cage-like structures of water ice with methane molecules trapped inside. Clathrate hydrates are powerful thermal insulators, with a thermal conductivity about 5 to 10 times less than ordinary water ice. They also have a much higher viscosity, roughly 10 times greater. Modeling suggests that a thin layer of methane clathrate at the base of the ice shell could act as a thermal blanket, trapping heat from the rocky core below and preventing the ocean from freezing out entirely. At the same time, this insulating layer keeps the ice shell above it cold and rigid, which explains how Pluto maintains the large thickness variations in its crust, like the thinned region beneath Sputnik Planitia. So Pluto likely has a present-day ocean of liquid water beneath its frozen shell, and it may have had one for its entire existence. And if Pluto started hot, then other large Kuiper belt objects like Eris and Makemake probably did too. Early oceans may have been common in the outer solar system. Some of them might still be there. Even in this cold environment, billions of kilometers from the sun, these worlds might have formed fast and hot, with liquid water from the very beginning. The implications are profound. If subsurface oceans are common among large icy bodies in the outer solar system, then the number of potentially habitable environments in our solar system is far larger than anyone imagined just a few decades ago. Not habitable for us, but habitable in the broadest biological sense, environments where liquid water persists, where energy sources exist, and where chemistry has had billions of years to do its work. When New Horizons looked back at Pluto after the closest approach, with the sun behind the dwarf planet, it captured one of the most stunning images of the entire mission. Pluto was backlit, silhouetted against the void, and surrounding it was a soft, glowing blue haze, layers of it. About 20 distinct bands, each a few kilometers thick, separated on average by about 10 kilometers, stretching up to 200 kilometers above the surface at visible wavelengths, and detectable in the ultraviolet up to 500 kilometers. The haze was optically thin but global. It wrapped around the entire limb, and it was brighter in the northern hemisphere, the summer hemisphere, by a factor of 2 to 3 compared to equatorial regions, suggesting greater aerosol mass there. Now, here is where things get interesting. The haze particles scattered light in a way that didn't make sense for a single type of particle. At visible wavelengths, the scattering intensity decreased gradually with longer wavelengths, suggesting tiny particles on the order of 10 nanometers. But those same particles also showed strong forward scattering, which is something only larger particles can do. And in the ultraviolet, the extinction cross-section was too large for even 100-nanometer spheres. One population of particles could not explain all of these observations at once. The solution came from a detailed analysis, combining data from all 4 instruments aboard New Horizons that measured the haze, the ALICE ultraviolet spectrograph, the LORRI wideband camera, the LISA infrared spectral imager, and the MVIC multispectral camera. When researchers ran a joint retrieval across the full wavelength range and multiple viewing angles, they found that the data required at least 2 distinct populations of haze particles. The first population consists of fractal aggregates, porous, irregularly shaped structures about 1 micrometer in size, built from small 20-nanometer monomers. These are responsible for the strong forward scattering and the large ultraviolet extinction. The second population is made up of smaller, more compact spherical particles with radii around 80 nanometers. These produce the backscattering that the aggregates alone cannot explain. This bimodal distribution was a surprise. Hazes in chemically reducing atmospheres dominated by nitrogen with trace methane, had always been modeled as a single, uniform population. The discovery at Pluto showed that even in these simple atmospheres, multiple types of haze particles can coexist, and it matches remarkably well with simulations of Titan's atmosphere. Saturn's largest moon has a similar atmospheric composition, and numerical models had predicted a fractal dimension transition near a pressure level of about half a pascal, where spherical particles begin coagulating into 2-dimensional aggregates. The sizes and shapes retrieved at Pluto agree with those Titan simulations at the same pressure level. But on Titan, the atmosphere is thick enough that the smaller particles eventually get absorbed into the larger aggregates before reaching the surface. On Pluto, the atmosphere is so thin, with a surface pressure of only about 1 pascal, that the haze particles hit the surface while they are still in the middle of this dimensional transition. The bimodal distribution is preserved, frozen in place. And this discovery has implications beyond particle physics. The haze controls Pluto's entire energy budget. The unexpectedly low atmospheric temperature, far colder than models predicted, was explained by efficient radiation from the larger, micrometer-sized aggregate particles. Solar energy, absorbed by atmospheric gases, is transferred to these haze particles through molecular collisions and then radiated away into space. The haze acts as a cooling system for the entire atmosphere. But the smaller population of particles, those 80-nanometer spheres, behaves differently. They radiate heat so efficiently that collisions with gas molecules cannot keep them at the same temperature as the surrounding atmosphere. The small particles may actually be colder than the air around them. This means the dominant radiative cooling pathway needs to be re-evaluated, and Pluto's energy balance may be more complex than anyone realized. There is another layer to this. Pluto's atmosphere changes with its orbit. As it moves further from the Sun, the surface pressure drops, temperatures fall, and more methane condenses out. The pressure level where the dimensional transition occurs will shift downward, eventually disappearing. The haze particles depositing onto Pluto's surface could be fundamentally different depending on where Pluto is in its 248-year orbit. New Horizons caught the atmosphere near its peak. By now, it is already fading. South of Sputnik Planitia, New Horizons found something that arguably nobody expected to find on Pluto: volcanoes. Ice volcanoes. Now, these are not like anything on Earth. They don't erupt molten rock. Instead, they appear to erupt a slurry of water ice, possibly mixed with ammonia and other materials, that oozes and flows across the surface. Scientists call this cryovolcanism. The most prominent feature is Wright Mons, a massive dome-shaped mountain roughly 150 kilometers across and standing about 4 to 5 kilometers high. That is comparable in scale to Mauna Loa, Earth's largest shield volcano. Wright Mons has a large central depression about 56 kilometers across and 4 kilometers deep. Nearby, there is an even larger feature called Picard Mons, about 225 kilometers wide and 7 kilometers tall at its highest points. Both of these structures have rugged, hummocky slopes covered in hills 10 to 15 kilometers in diameter. The texture is unlike anything else on Pluto. It looks almost like the surface of a boiling liquid that froze in place. Some researchers have compared it to pillow basalts, but on a massive scale. What makes this so strange is that the surface of Wright Mons has almost no impact craters. That means the terrain is geologically young. Estimates put an upper age limit at roughly 1 to 2 billion years, but many features could be considerably younger. Some researchers suggest the most recent eruptions may have occurred only a few million years ago, and there is chemical evidence too. Spectral analysis of regions associated with cryovolcanism at Virgil Fosse, at Kiladze caldera, and on the slopes of the large mountains, has detected signatures of ammonia and water ice enriched with reddish organic compounds called tholins. Ammonia is significant because it acts as a powerful antifreeze, lowering the freezing point of water and allowing the material to remain mobile at Pluto's extreme temperatures. But ammonia is also unstable on the surface. It gets destroyed relatively quickly by ultraviolet radiation and cosmic rays, so its presence suggests that these features are not ancient. They are recent. The driving force behind all of this is thought to be Pluto's internal heat, generated primarily by the decay of radioactive elements in the rocky core, along with residual heat from formation and energy released by the slow freezing of the subsurface ocean. When water freezes in a closed subsurface reservoir, its expansion can create sufficient pressure to squeeze the remaining liquid up through cracks in the crust. Dissolved gases like nitrogen, methane, and carbon monoxide can also form bubbles during ascent, reducing the density of the cryomagma and making it buoyant. Tectonic stresses from Pluto's global expansion, combined with the massive loading of ice at Sputnik Planitia, may have opened deep faults that served as conduits. Models suggest that the weight of Sputnik Planitia could promote cryomagma ascent in a ring zone around the basin, which is exactly where Wright Mons and Picard Mons are found. The morphology of these mountains suggests they did not form from a single eruption. Instead, they may be the result of multiple, separate eruptions from numerous smaller sources that merged over time. The smaller dome, called Coleman Mons, about 25 kilometers across and 1.5 kilometers high, may represent what one of those individual eruptive centers looks like before it merges with its neighbors. Nothing like this exists anywhere else in the visited solar system. To understand why Pluto looks the way it does, you have to understand its orbit. And its orbit is unlike anything in the inner solar system. Earth's axis is tilted at about 23.5 degrees, which gives us our relatively mild seasons. The Moon helps stabilize that tilt, keeping our climate within a narrow, livable range. Pluto has no such luxury. Its axis is tilted at 122.5 degrees. It is practically lying on its side. This creates enormous Arctic and Antarctic zones, regions that experience continuous sunlight for decades, followed by continuous darkness for decades, and it drives extreme seasonal cycles that have no parallel anywhere on Earth. After the last equinox in December 1987, Pluto's North Pole exited its 4-year-long polar night. Nitrogen ices at the North Pole began to sublimate, entering the atmosphere and condensing at the now dark South Polar region. The entire atmosphere is in sublimation and deposition equilibrium with surface nitrogen ice. So even small temperature changes of a few degrees can cause the surface pressure to shift by orders of magnitude. Think about that for a moment. A few degrees of warming and Pluto's atmosphere can become 100 or even 1,000 times thicker. A few degrees of cooling, and it collapses onto the surface as frost. Pluto's orbit is also highly elliptical. It swings as close to the Sun as 30 astronomical units, which is actually inside the orbit of Neptune, and as far away as 50 astronomical units. Surface temperatures vary between roughly 40 and 60 Kelvin, which is close to the condensation points of nitrogen at 32 Kelvin, methane at 45 Kelvin, and carbon monoxide at 52 Kelvin. These are not temperatures that leave much room for error. A portion of the atmosphere literally condenses out and falls as exotic snow when Pluto is farther from the Sun. The coldest regions on Pluto, on average, are not at the poles. They are at about 30 degrees north and south latitude. Early in Pluto's history, ice tended to accumulate at these latitudes in a runaway process. More ice meant higher albedo, which meant lower temperatures, which attracted still more ice. Over about 1 million years, simulations suggest this feedback loop would have collected most of the volatile ice into a single cap, even without a pre-existing basin. When New Horizons visited, Pluto had recently been at perihelion, its closest approach to the Sun, which occurred in September 1989. The images we have are of Pluto in its warmest, most active state. The glaciers flowing, the haze glowing, the atmosphere at its thickest. Pluto has since continued along its orbit, moving away from the Sun. The atmosphere is condensing, the surface is changing. But the spacecraft is long gone, and no one is there to watch. The New Horizons flyby transformed Pluto from a barely resolved dot in the sky into one of the most fascinating worlds in the solar system. We found convecting glaciers of nitrogen ice that are younger than some cities on Earth. We found evidence of a liquid water ocean that may have existed since the day Pluto was born. We found hazes with a bimodal particle distribution that rewrites our understanding of atmospheric chemistry on cold, reducing worlds. We found ice volcanoes the size of Hawaii's largest mountains, erupting water and ammonia slush onto a surface where the temperature is 200 degrees below anything on Earth, and we saw only half of it. The flyby was restricted to one hemisphere, observed over a matter of hours. The far side of Pluto remains a mystery. We do not know what geological features exist there. We do not know if the cryovolcanic terrain extends further south into regions we could not image. We do not know how the surface has changed in the decade since New Horizons flew past, as Pluto moves deeper into its long, cold winter. The next step is an orbiter, a spacecraft that could circle Pluto for months or years, imaging both hemispheres in full, measuring the gravity field to confirm or deny the ocean beneath, and watching in real time as the atmosphere condenses and the exotic snows fall. Earth-based observations continue to monitor Pluto's atmosphere as it races farther from the Sun. But without up-close imaging, we can only guess how the surface is changing. Compared to the relatively warm surface imaged in July 2015, a future mission may reveal a completely different face of Pluto, hidden beneath a blanket of exotic snow. Pluto's northern terrains are heavily cratered, suggesting they formed about 4 billion years ago. Ancient parallel canyon systems, now eroded by glacial activity, record a period of early extensional tectonics. Dendritic valleys cut through the northern highlands, carved by the deposition and transport of seasonal ices. These features tell us that glacial action has been reshaping Pluto's face for a very long time, perhaps annually, driven by seasons dramatic enough to produce notable changes over the course of its 248-year orbit. What we know for certain is this: Pluto is not a dead world. It never was. Beneath that thin, frozen crust, something is stirring. An ocean, perhaps as old as the solar system itself, kept liquid by an insulating blanket of methane clathrate, driving ice volcanoes and refreshing the surface of a world that has no business being this active. The more we study Pluto, the stranger it becomes. Every answer brings another question. And that is exactly how science is supposed to work.